Hey guys, today we're going to be talking about Coulombic attraction and ionization energy and how they relate into the photoelectron spectroscopy. So what is Coulomb's law? Coulomb's law compares distance and charge of molecules to explain the electrostatic force of attraction or repulsion between them. In the formula, Q represents the charge product of the molecules, and it's more influential over ionization energy compared to the distance between the atoms, which is represented by d squared in the denominator on the equation on the right. So what is ionization energy? It's the energy required to remove an electron from orbit, and valence electrons will be removed first due to Coulomb's law. For example, aluminum. There is a jump in the ionization energies of aluminum after the third ionization energy because aluminum has 3 valence electrons. After that third ionization energy, you start to remove core electrons. And it takes more energy to remove the core electrons due to increased nuclear attraction and decreased shielding effect, and that results in increased Coulombic attraction according to the formula of Coulomb's law. Here are some ionization energy trends. Generally, it increases going across a period and increases going up a group. That's again because of the shielding effect and Zepf number. Going across a period, the Zepf number increases with the amount of protons, and as you go up a group, there is less electron shells and less shielding effect, which means there is more attraction to the nucleus. There are some exceptions, like noble gases. Fluorine has a higher electronegativity value than neon or helium because noble gases have a filled outer shell of 8 electrons, and so that kind of prevents them from gaining electrons because they're already stable. Also, half-filled and completely filled orbitals result in higher ionization energies because their electron configuration is already stable. So removing an electron results in increased repulsion. For example, nitrogen has a higher ionization energy than oxygen. Thus, group 2A and 5A are usually more stable than the groups next to them. For example, beryllium, magnesium, and calcium in group 2A because beryllium has a stable configuration of S2 and requires more ionization energy. To find exceptions in ionization energy, you have to look at their electron configuration. For example, on the left is what is expected for ionization energies according to atomic number, because atomic number represents the number of protons. So as you increase that, it should have a higher ionization energy. However, that does not always match, as you see on the graph on the right. So why? It's because nitrogen has a half-filled 2p shell, which is more stable than oxygen, who has a 2p4 shell. Thus, it is easier to remove an electron from oxygen to increase stability. This also explains why boron has a lower ionization energy than beryllium. So, photoelectron spectroscopy. The charge product and Zepf number influences the energy required to remove an electron, and the height of peaks represent the number of electrons. And with a higher Zepf, proton attraction and nuclear penetration results in a higher binding energy, and the peaks will be closer to the highest energy on the x-axis. For example, nitrogen's configuration is 1s2, 2s2, and 2p3. As you see on the graph, the 1s2 energy level is closer to 100, and as you expand to outer valence electrons, it requires less energy to remove them. If you look at the height of the peaks, 1s2 and 2s2 have the same height due to having the same number of electrons in that shell, but 2p3 has an additional electron, so the peak is going to be higher. Here we have hydrogen versus helium. Similarly, hydrogen has a smaller peak than helium because it has less electrons. And the helium peak is further to the right, which means it has higher energy, and more energy is needed to remove the 1s electron. So, it's held more tightly because there is a higher effective nuclear charge, or Zepf number. And in the PES graph, you can compare different elements using their ionization values. The graphs compare Coulombic attraction by comparing binding energy. A higher binding energy indicates increased Coulombic attraction due to either a higher Zepf number or a smaller distance between nuclei of atoms. So how is it applied? There are 2 categories: ultraviolet photoelectron spectroscopy and X-ray photoelectron spectroscopy. And XPS is also known under its former name of electron spectroscopy for chemical analysis. The UPS focuses on ionization of valence electrons, while XPS is more specialized towards ionizing those core electrons, which are harder to remove. The main goal of both of these is to determine either composition, electronic state, chemical state, binding energy, and on the surface of solids. And you can determine the measurement of molecular orbital energies to be compared to theoretical values calculated from quantum chemistry. We all remember the quantum numbers, or maybe we don't, but that's not my video. So determining bonding, non-bonding, and or anti-bonding molecular orbitals can also be determined. And we've gone over that too when we drew our diagram showcasing anti-bonding versus bonding. And the binding and orientation of absorbed species on the surface of solids can also be determined, and band structure mapping in K-space. And here we have a diagram of how exactly the machines work to produce our results. And some more real-world applications. So you can analyze stains and residues on surfaces at crime scenes from looking at their binding energies. You can also you can test the reactivity of frictional wear of solid-solid reactions. You can use it in depth profiling, which is actually used in the composition of thin films because you can analyze very small sections of matter using this XP spectrometer. And it's also used for imaging of surfaces and determining the distribution of elements in surface structures. And that's it, guys.